Okay, good morning. Let's start with this. I have CE Pune in front of me on the screen. Good morning, guys. So I said you all are sitting in an auditorium, but what you're going to watch is not going to be as entertaining as a movie. So let's continue from what we did last time. So to quickly summarize, what we did last time was just two things. One is we defined electric field, electric flux density, and we defined Gauss law. So we defined Gauss law, and we defined both the point form, or we derived both the point form and the integral form. The point form, to remind you, said that divergence of D is rho, the volume charge density, and the integral form said that the closed loop integral of D dot ds, closed surface integral, is the charge enclosed. After this, we defined potential as the work done in moving a unit charge in the presence of an electric field. Then we defined current density J, and we said the sources of current in the system could be conduction current or a convection current or a displacement current, about which we will do in the later class. Now, using this idea of Gauss law, which is purely in a, you have static charges, means charges that are stationary. Now, the next logical step would be to do the next Maxwell's equation. This is the next logical step would be to do the next Maxwell's equation, but I'm going to take a small detour and tell you an application of using this Gauss law, and the application that I'm going to do is related to the motivation why we are doing these Maxwell's equations. At the beginning of the course, as I said, we are electrical engineers, try to use this to be applied to high frequency circuits. We started doing transmission lines and transmission line model, and we stopped there at the point where we said, look, we need to find out what is the inductance per unit length, capacitance per unit length, conductance per unit length, and resistance per unit length. Want to be finding out all that, and to be able to find out all that, we want to be learning about charge and electric field and magnetic field and so on. So I'm going to take a small detour from here to say how this Gauss law would help you to calculate capacitance per unit length. So we go back to the example of a transmission line where this is your inner conductor, you have the outer conductor, and let us say you are connecting the inner conductor to the outer conductor. To keep it simple, let's do this as a DC voltage. All right. So if I apply a potential, what happens is there could be charges accumulating on this conductor, positive charge here, negative charge on this conductor. Let us say the radius of the inner radius, if I draw the cross section, the inner radius is A and the outer radius is D, and I have, let's say, charges plus on the inner conductor, minus on the outer conductor, and between the inner and the outer conductor I have a dielectric. This is the structure of a typical transmission line. Question is, what is the capacitance here? So I am trying to find out in a simple way what is the capacitance of a cylindrical capacitor. You can think about the transmission line now as a cylindrical capacitor as opposed to a parallel plate capacitor. In a parallel plate capacitor you have two plates and dielectric in between. The cylindrical capacitor, you have, this is your metal, this is also your metal, and between the region you have a dielectric. So what we are going to do is we are going to use Gauss law. Since I want to find the capacitance of the region between the two plates or the system which has two plates, I can say that I have an electric field E or D which runs from, for this instant where this inner conductor has accumulated positive charges, I have a D pointing from the inner conductor to the outer conductor. So question is, should I use the point form or should I use the integral form? I'll use a point form if I want to know what is the evolution of field and things like that. So use an integral form and then demand that I would apply Gauss law on a surface which I am drawing here. So I am going to be applying Gauss law on a surface and I am choosing a cylindrical surface. Why am I choosing a cylindrical surface? Choosing a cylindrical surface, or I am choosing that surface which is symmetric to the system. So I am using this cylindrical surface, and on this cylindrical surface what we are going to do is to apply Gauss law, the integral form of the Gauss law, which says surface integral d dot ds, the closed surface integral d dot ds is the charge enclosed, which simply means that there is a flux that is coming out. I know the flux density, or rather I want to find the flux density. The flux density is such that if I take the total flux which is coming out of this surface, that should be equal to the charge enclosed by the surface, in this case a positive charge here. Why am I using Gauss law? My plan is to do this. I will use Gauss law and find D. Once I know D, I find E, the electric field density. Once I know E, I find potential. Once I know the potential, I am going to use this relation Q is equal to CV and find out capacitance. This is the plan, right? So you are trying to find the C, the capacitance per unit length of the transmission line, and the plan is to do in this fashion. This is the algorithm. To find D, you are using Gauss law. All right. So how do I use Gauss law now? I know that because this inner conductor is positive and the outer conductor is negative, I have an electric field and hence a flux which is pointing from the inner conductor to the outer conductor. So my D is radially outward, and because it's a cylindrically symmetric system, what we would do is to use a cylindrical coordinate system. So if I turn this capacitor around and I align it along the Z axis, I am trying to draw how the cylindrical coordinate system corresponding to this loop is going to look like. So I have, let me try to draw this first. This is the surface of the cylinder. You know that in the cylindrical coordinate system, we imagine that the points that we want to describe is falling on the surface of a cylinder. So let us say the points that we want to describe is here marked in red, point P. 3 unique coordinates are R, phi, Z. So the height of this point from the origin is defined as the Z coordinate. The distance of this point from the Z axis is your R coordinate. The unit vector in the direction of R is here, AR. Unit vector in the direction of Z is AZ, marked in the red arrow. And the third coordinate that uniquely defines this point is the azimuth, the angle that this point makes with respect to the projection of this point on the XY. The projection of this point on the XY plane, the angle that line makes with respect to Z axis. This is the phi. So for another point on the cylindrical coordinate system, for example, if I am considering the point along the same radial coordinate, what would be, and the same Z coordinate, what would be different is the angle. All right. Now, should I shift to the board? I can do that. Let's see. So now, what would be the unit vector in the direction of phi? Phi is this angle. The unit vector in the direction of phi is here. All right. So I'm going to be using this cylindrical coordinate system to describe this problem. So I repeat, this is the point, the distance that this point may The distance of this point from the z axis is your r coordinate. I take a projection of this point on the xy plane, and the distance made by that, I'll change over to black. Okay, this computer is playing up, so I'm going to change over to blackboard. Okay, so I need the choice here. Okay, so this is my this side from here. Okay, from this side. So this is the point that I want to describe. This is my z axis, this is my x and y. So the distance that this point makes, this point from this is your r coordinate. The height of this point is your z coordinate. So unit vector in the direction of z, this is your az, this is your ar. Now the angle made by this point with respect to the azimuth angle is your phi. So how do I know what is my azimuth angle? I take the projection of this on the xy plane, and the angle made by this projection is your phi. It's your phi coordinate. Now, since this is your phi, is that coming clear? I have to write little more bigger. Okay. So my a phi is in this direction. Okay. So as I discussed, to find, see, what we are going to do is to find D and hence E. Once I know what is E, I have to find the potential, and once I know what is the potential, my C is, Q is CV, so C is Q over V. This is the plan. And to be able to find D, I'm going to use the Gauss law. So this is my inner conductor, this is my outer conductor. Given instant of time, I assume that this is positive, this is negative, which is my Gaussian surface. My Gaussian surface is a cylinder. And why did I choose the cylinder? I chose a cylinder because that is what is symmetric, or that is the surface of symmetry for this problem. Now, what is the direction of D? I want to be using this relation, closed integral D dot ds is charge enclosed. I do not know what is the charge enclosed in this. So what I am doing is, I am defining line density of charge as rho L. I say that per unit length the charge is rho L. So line density is charge per this size is okay? Yeah. This is the charge per unit length. Let me say that. And to be able to find this integral, I want to be able to write down what is D vector, what is ds vector. Now what is D vector? This is plus and this is minus. I know that D is epsilon E. We are talking about an isotropic medium, so the direction of D is the same as the direction of electric field. What is the direction of electric field here? This is plus, this is minus, so the direction of electric field is this. I turn this around, this is my z axis in my cylindrical coordinate system, this is my r direction, so this is my AR direction, this is the AR direction. So my D is only in the AR direction, so I call this as dr, the component of D along the direction of R, this is the radial direction, that I call as dr, times the unit vector along AR. What about ds? Suffix D. Now what is ds? ds is the surface on the elemental surface on this Gaussian surface. So what is the direction of ds? That has to be along this. That is also, it is the direction of the outward normal. The direction of this is also along AR. What is the magnitude of ds? To find the magnitude of ds, let me draw it bigger because they say that you are not able to see it probably properly. So to tell you what is the direction of magnitude of ds, this is my phi. Where is my ds? ds is this elemental area with its direction which is pointing outward, which is along R. So this is my x, y and z, this is my R, and this area, how do I find this area, this red hatched area? Its length is an elemental length along the z axis, so its length is dz. But what about its breadth? That is approximated as this length, right? And what is this arc length? So if I consider the point P here and I am moving along this line through a small angle dphi, then this length is simply the arc length, and that would be r d phi. So my element area ds has a magnitude AR, but the magnitude has a direction AR. Magnitude is the area of this, which is length times r d phi. Alright. So this is my ds. So I know what is d and ds, so I can use now Gauss law. And this is the part or the section of the cylinder in which I am applying the Gauss law. So I want to use this for the closed surface integral. So which means I have to imagine that this cylindrical section is now has to be closed. So when you are closing this, what would be the limit of integration for phi? When I want to do this integration, phi has to go from 0 all the way, it has to completely close, which means 0 to 2 pi. This 0, from 0 it has to go all the way to 2 pi. What about r? Or what about r limit? We are not bothered about because we have an elemental length dz now to worry about. Dz is along the z axis. Let us say the length of this element is L, so dz is from 0 to L. So if I rewrite this, that would turn out to be double integral dr AR, which is my d, ds is dz r d phi AR, the dot in between, equal to the charge enclosed. Now what is the charge enclosed? If I am considering an element length L, and if rho L is the charge per unit length, this would be rho L times L. What are the limits of integration? I put a double integral because it's a dz and d phi, with phi running from 0 to 2 pi to close the surface, to close the surface in this direction, and to close the surface along the length, my z should run from 0 to L. Now I have to do this integration. So you see the elemental, the variables of integration are z and phi. So if I integrate z from 0 to L, I will get L. If I integrate phi from 0 to 2 pi, I will get 2 pi. So my answer would be, and AR dot AR is 1. So I have dr 2 pi times L is rho L times L, which means my dr is rho L divided by 2 pi. So my d is rho L divided by 2 pi in the direction AR. So I got my d. Once I get my d, what is E? D over epsilon, which means this rho L over 2 pi epsilon AR. I have my E. What is the next step? The next step is to go and find what is V. So to do that, I need a clock. So I am going to do this step. Your potential is, we derived yesterday that potential is minus E dot dl. We are finding out the potential between the inner conductor and the outer conductor. Inner conductor has radius A and the outer conductor has a radius B. So this would be minus integral A to B rho L over 2 pi epsilon AR. What about DL? Now DL is the, you are going from the inner to the outer conductor. So what is DL? DL is the elemental length in the direction of your path. Your path is along AR, which means this is dr AR. Well, I missed an R here. There is an R sitting here, so there is an R here, which means there is an R here, means there is an R here. Out of which AR dot AR is again 1. Your integration would now reduce to calculating minus integral A to B rho L by 2 pi epsilon. This is a constant dr over R. I do this, this would be integral dr over R is ln of R with B to A. There is a minus sign of course here. This is my potential. Well, what does this minus sign indicate? This indicates that this is my inner conductor, this is the outer conductor. In the instance we considered, this is plus, this is minus. So I have my E field from the inner to the outer conductor. This V is negative or positive depending on whether you are trying to move the charge from the inner conductor to the outer conductor or from the outer to the inner. What does this negative indicate? It simply indicates that if I am moving the charge from the inner conductor to the outer conductor, which means in the direction of the electric field. The work is done by the electric field, because as you know, electric field is experienced by the unit charge. So if you are moving in the direction, the work is done by the electric field. Whereas if you are going from outer to inner, you have to work against the electric field to move the charge. So this minus sign is indicating only the fact that you are moving against the electric field. That's the meaning. So when you calculate capacitance, which is the fourth step, C is Q over V, I don't really have to worry about this minus sign, because that is only telling you the direction, whether the work is done by the field or whether the work is done on the field. So if I do this, what do I get? Q over V. Now what is Q? Q would be rho L times L, the charge, or I could replace this rho L as Q times L, the charge times the total length. So Q over V would be Q over Q times ln B by A, and I will have a 2 pi epsilon L in the numerator. And remember, transmission lines, we were defining capacitance per unit length. So capacitance per unit length would be 2 pi epsilon over ln B by A. So this is how we would use the Gauss law that we learned to find the capacitance per unit length of a transmission line. The strategy was simple. Calculate, use, you to be able to use Q over V, you wanted to find potential. To find potential, you wanted to find field, so you found the flux, and Gauss law is helping you to find the flux. You could repeat this calculation for any kind of transmission line. Alright. So since we have done this, we have used this to find the capacitance per unit length of the transmission line. What we could do next is to move on and what is the next thing that you want to find for a transmission line? You want to find the inductance per unit length. Now to find the inductance per unit length, you know that inductance is related to flux. Flux is proportional to, the magnetic flux is proportional to the current. What it means is that if I have a current carrying conductor, I know that there is a magnetic field around it, Oersted observation, and the flux due to the magnetic field is proportional to current, and flux is equal to inductance times current. So inductance gets defined as flux per unit current. So to be able to find inductance, I should be able to find flux, where phi is your magnetic flux. So I should be able to find the magnetic flux. So I should know what is the magnetic field to find magnetic flux. So the information that I have is only about the electrostatic field. I need to be able to find what is the magnetic field now. So to reach this goal, we want to be able to find H, or magnetic field intensity, similar to E, and we want to find B, which is the magnetic flux density due to a current carrying conductor. This is analogous, field intensity is analogous to E, flux density is analogous to D in the electrostatics. Want to be able to find these two to be able to find L. Now how do I find these two? So for that, we start with the Biot-Savart's law, which says that if I have an elemental current carrying conductor which is carrying a current Di, of course we know Hans Christian Oyster's observation that a current carrying conductor would always produce a magnetic field around it. If I send a current through a conductor, I keep a magnetometer or a magnetic compass next, it will start deflecting whenever there is a current. Now, to find at an arbitrary point P, you want to find out how much is the magnetic field. What is the magnetic field induced? That is given by Biot-Savart's law. And the Biot-Savart's law states that dH due to an elemental current Di, dH due to an elemental current Di is of course a vector whose magnitude is dependent on r, the distance from the point of observation to the current carrying element r, and whose direction is given by the direction of unit vector in the direction of the line joining the point to the current, it is AR in this picture, and this is current times, well, let us say I have current I times dl, which is your Di, cross r is the vector in this direction, dl cross r divided by 4 pi r square, using the same r everywhere. So this is a vector whose magnitude is given by IDL, which is Di, times r, this distance, divided by 4 pi r square, and the direction is given by the direction of the cross product of dl cross r. So magnitude is proportional to current, inversely proportional to the square of the distance. Now, in fact, if I look at the magnitude, this r also has r. So this r also has magnitude r and direction r. So if I can split, I will actually have 1 r less in the denominator because this would cancel out. So h is actually inversely proportional to not r square, r. Now let us try and find out what is the direction of h. dl is in this direction, the elemental length is in this direction, r is in this direction. So dl cross r, so I have this is my direction of dl, this is the direction of unit vector r. So dl cross r, if I were to find what is the direction of the cross product, you know that the cross product, if I have a vector A, have a vector B, A cross B, to find the direction of A cross B, I use my right hand rule. I move from A to B, direction of the thumb, I curl from A to B, the direction of the thumb is the direction of A cross B. So same here, I move from DL to AR, my direction of the thumb is going into the plane of the board, which I represent as an into. An into mark would mean into the plane. So at this point P, if I do DL cross AR, it is into the plane of the board, right? Now if I think about all those points which are at the same distance, which is along this circle, I think about it as a cone and I am sweeping all the points on the surface of the cone, all of them would have the same r from dl. and so all of them would have the same magnitude if I scan over the rim of this cone, because all of them are having the same distance. But do all of them have the same direction? Let's say I take a point P here or P prime here, and let me calculate. Let me try and find out what is the magnitude and direction of magnetic field. Magnitude is the same because, as I said, along this cone R is the same. But what about AR? AR is in this direction now, which means I have for this point P prime, my AR is in this direction. So if I do DL cross, DL is along the yellow, AR is now in this direction. So if I do DL cross AR, I have my direction of the cross product pointing outwards. So pointing outwards is what I would represent like this. So on this surface I have H pointing inward, this surface I have at this point I have H pointing outward. Now I keep calculating what is the direction of H at all the intermediate points. It will turn out that the direction of H is changing, it is curling, it is turning. So if I look from the top, this is my point P and the direction. So this is if I look at it from the top, which means my DI is, let's say, if DI is pointing outward, my H here is in this direction because my DI is pointing outward. So the direction of H is like this, and here the H has reversed. So if I keep drawing the direction of H at all the points here, it will start doing this. In other words, remember our discussion on curl. This is an example where the vector is curling around, which has a large curl around this current. I hope you understand this. I can repeat here. At this point, your R vector is in this direction, DL vector is in this direction. So DL cross R will be into the plane of the board. At this point, R vector is in this direction, DL is here. So DL cross R would be DL, this is my DL cross AR, that is pointing outward. Which means if I trace this rim of this cone, the circle, every point the H is changing its direction. It's into this here, it's out of the plane of the board here. So if I draw the same thing by looking from the top, it would mean that this, so my current direction is outward, H is in this direction, H is continuously, so this arrow marks I'm doing the direction of H. Remember, the size of my arrows are all the same because the distance of all these points from the current carrying element is the same. So the magnitude of H is the same, right? So this is how one can calculate H given the current, and this H is measured in amperes per meter. It has to be in amperes per meter because I is in the unit of ampere. You will have, this is elemental length, so you will have it as ampere per meter. Now we can talk about Amperes law, which states that if I take the loop integral of, H, closed loop integral of H, then that closed loop integral should be, you see, H is because of a current in the loop, and so Amperes law simply states that the closed loop integral of H is the current enclosed. which is similar to Gauss law, which says that the flux density is equal to the charge enclosed. Because flux density, electric flux density was because of the presence of the charge, and the total flux density was equal to the charge enclosed. That was Gauss law. Amperes law states that my magnetic field intensity is because of the presence of the current, and so if I take a loop integral of H dot of the magnetic field, that should give me the current enclosed. That is Amperes law. Now I can use the Stokes theorem, where when we talked about curl, we talked about Stokes theorem, where we said that loop integral of a vector function is nothing but I can take the curl of the vector function and take this as a surface integral. The loop integral can get replaced as I keep taking the curl and I integrate over the surface, that will give me the loop integral. That is equal to, now last time when we discussed current density, we also said that current can be written as J dot ds, surface integral J dot ds. So I am able to replace, because current density is current per area, so if I integrate current per area over the area, I should get the total current. So equating these, if I take the same area, I get, equating these two, I get del cross H equal to J, which is again one of the Maxwell's equations for magnetostatics. Curl of H is J. Before I close the class today, also say how do you relate magnetic field density to H? B is mu times H, where mu is your permeability of the medium here. You see, H is independent of the medium. It did not bother to tell what the medium is between the current carrying element and the point under consideration. It could be any medium. Irrespective of the media, H is the same, does not care what the media is. But the effect of the presence of the media, whether the flux is able to penetrate, how much is the flux is able to penetrate, that is given by magnetic flux density, which is mu H. So what we did today, to summarize, first of course we used Gauss law to find out what capacitance per unit length for a transmission line. The next thing is we said was we will try and attempt to find what is the inductance per unit length, and we got back to look at what is our understanding of inductance. Turns out that to find inductance you need the magnetic flux density. So we got on to magnetostatics, and to start with I discussed Biot-Savart's law with you, which tells you how to calculate the magnetic field due to a current carrying element. We also discussed how to find the direction of magnetic field, and that how it is curling around the current carrying conductor. And we discussed Amperes law, which is simply a restatement or a qualifier for Biot-Savart's law, which says that the total magnetic flux, if I consider this loop integral, that is equal to the current enclosed. Another way of saying it is the curl over the total surface is equal to, or the curl of magnetic field by how much it curls is decided by the current. So an easy intuitive way of understanding this is the following. I have current carrying element, I know that there is a magnetic field around it. I also know that the magnetic field is curling around the current carrying element. If I understand what curl is, I know that curl tells you by how much is the vector rotating. So this is telling you exactly by how much is the H vector rotating. It is telling you that the H vector is rotating by an amount which is equal to J. More is the J, more would be the rotation. More is the current, more is the rotation. That's how you can intuitively understand or remember this last, this is the last Maxwell's equation. Curl of H is J. Again, this is for magnetostatics. which means that we are not considering any time variation for electric field or magnetic field yet. The moment you have electric field or magnetic field variations, there will be a slight modification here that we will deal with later, but for magnetostatics the Maxwell's equation is curl of H is J. We also, so to summarize the Maxwell's equations that we know until now, we know the Gauss law and we know the Amperes law. In the point form, the integral form is this. In tomorrow's class, what we will do is we will go back to this business of finding what is L, because now I know to find how to find magnetic field intensity. So I know how to find magnetic flux density from here, and then I will calculate what is L. That is what we will do first. Then we will finish up on the Maxwell's equations. All right. We'll stop the class here. The class is open for questions. If there are any questions, please hand raise or type your questions in the question window or chat window. CE Pune, do you have any questions?
प्रश्न केले पण ते त्यांनी विचारायचं त्यांनी आपल्याला फोकस केलं म्हणजे ऑल दिसणार. Okay.
I have a question here. Why is the unit of surface current density for why is the unit of surface current density ampere per meter and not ampere per meter square? In fact, surface current density, if you look at J dot ds should give you amperes, which means J should give you ampere per meter square. It is indeed ampere per meter square. Any other questions?
इंटरेक्शन होना चाहिए थोड़ा एक्शन के जैसे पूरा
There are no more questions. We will log out and meet you tomorrow. Meet you on Thursday.